Okay, so hello everyone. My name is Will Schober. I'm a PhD student at the Università della Svizzera, Italiana in Lugano in Switzerland. And this is a joint work with Scott Wesley from Dalhousie University in Halifax, Canada. So I'm going to be telling you about this thing that we call a hierarchical circuit language, which is really just a kind of slight extension of quantum circuits that capture a couple interesting things, in particular control, or describing controlled operations as a composition. Okay, so for a bit of motivation, okay, there's several motivations here, but maybe one of them is for control flow. So on the left, I've got the same diagram that we saw in the keynote speech. This is the coprocessor model, where the idea is that you have a CPU that is sending instructions to a QPU, and so inside that CPU would be a programming language. It has classical control flow, it has a compiler, and so on, and it's just sending unitary instructions to be carried out on a quantum processor. So like on the right side here, I've got some examples of things you can do, or rather 3 examples of things you can do and 1 example of a thing that you can't really do. So you can sequence a unitary instruction. You could do classical controlled unitary instructions. So you have classical control in the CPU that decides whether or not to send this instruction V. In modern programming languages, they're starting to do these hybrid programs, as we've heard about a couple of times. So like Guppy from Quantinuum, they've worked quite a bit on this, where you have feedback back and forth. So you might do something like send an instruction to do a measurement. Then the measurement returns back to the CPU, enters the classical control flow there, and ultimately decides whether or not to sequence this unitary instruction W. The last one, the controlled Y, is something that you can't really do. And I'm being a little facetious when I say you can't do it, because, okay, it's a unitary. You can always just send it as a unitary instruction. But in this coprocessor model, you don't really have quantum control flow. You just have classical control flow, which means doing this really as a controlled operation isn't really possible. There's been a fair amount of work talking about this in the last year or two. So for example, this paper, where you can read more about why upgrading classical models of control flow to quantum is not so easy. Okay, but then I'm going to talk about this circuit language where we, among other things, we've got a generalization of this notion of controlled operations because we're interested in studying them. Why? Because, oops. Sorry, my computer went to sleep. Ah, there we go. Why? Because, well, those are kind of universal in circuits. I mean, people use them in algorithms all the time. Okay, so the first couple slides here, I'm just going to talk about the mathematical formalism. This comes from category theory. We're modeling circuits as a prop. A couple people have talked about this already, so I go sort of quickly through it. But so this is just a way to describe what a circuit is. So in this prop formalism, you describe a language, so a family of circuits, basically as a collection of generators. These are just named boxes, so they have a name G and they have a signature N, which is just a number of input wires. You specify those, and then you also, of course, typically specify the semantics, which here is going to be unitary matrices because we're talking about quantum circuits. You always get these two for free. You get the identity wire and the wire crossing, which have these semantics. And then lastly, you have these 2 compositions, the sequential composition and the parallel composition, that you use to basically construct circuits. And they have the usual semantics of matrix multiplication and tensor product or Kronecker product. I put U and V here because these are arbitrary subcircuits. So the idea here is that you construct the prop by just kind of freely composing with either the sequential or parallel compositions. So here's an example of what that looks like. This formalism was developed mainly by a group in Nancy. So this is the same gate set that is used by a couple of those guys. And yeah, the idea here is, okay, well, you have, like, for example, this generator H and this generator Z, which actually here is parametrized. So it's kind of an infinite family of generators, but that's fine. And because these are both in the language, you can compose them, and then that's now a subcircuit that's in the language. You can do the same in parallel. So these 2 are in the language, and this one is in the language. So the parallel composition of them is also in the language, and so on. And you basically just tile a circuit. So that's how the prop formalism works. What we did is basically slightly extend this. So we're using the same base prop, but then we're kind of adding 2 new compositions to capture some new stuff. So here they are. So they look like this. The first one here is meant to be subcircuit exponentiation. And semantically, it's just basically raising a matrix to a arbitrary real power alpha. I write it this way. I don't know if this is so familiar to everyone, but it's just exp is the matrix exponential, and then log is the complex matrix logarithm. I put a capital L here because it's putting every eigenvalue into the principal branch. That's a little detail, but it turns out to be relevant. And yeah, this is the first line there is really nothing new. I mean, that exists in literature. In fact, it even exists in practice. I think in OpenChasm 3, this was already implemented. There's something called the power modifier, and I'm pretty sure it's doing exactly that. So there, we're just kind of giving a name to something that already exists. The second line, I pause on a little bit because it's a little more new. So this funny thing is what I'm going to call the control product. And it looks a bit like a parallel composition in the sense that you take 2 arbitrary subcircuits on n qubits and m qubits, and you draw a vertical line between them. And it carries this semantics, which is it's a bit strange. What we're doing is taking the logarithm of the 2 matrices involved, tensoring them together. We're dividing by ipi, which is just a kind of normalization, basically to return you to the principal branch. And then we're exponentiating the whole thing to get back to a unitary. And I'll show you in the next slide or two that this does, in fact, generalize the notion of a controlled operation. So this doesn't exist in the literature as far as I know. However, earlier this year, I was at QIP in Raleigh showing this as a poster, and Craig Gidney from Google came up to me and said, I recognize this. I had this idea back in 2017, and I wrote about it on a blog post, but never found anything to do with it. Oops. Never found anything to do with it. So this is a screenshot from that blog post, and you can see the definition is exactly the same. And he says, but I digress since I haven't found a thing for which the above idea adds clarity. So another way of looking at this talk is we're trying to find a way to use Craig Gidney's idea. Okay, then how do you actually construct this kind of modified prop with these 2 extra operations? The idea is basically the same. So in the previous version, we just kind of compose freely with the 2 operations. Here we do that as well, but then we also kind of compose freely in these 2 extra operations. So okay, what can you do? Let's do the exponentiation first because it's kind of easier. So here's some gate set that I'm taking as my base gate set. It's got, I don't know, this one that has no inputs and these 2 that have 1 input, and they have some names. So for example, since, I don't know, this gate is one of my generators, okay, I can do this, and it's also in the language. But then you can also exponentiate an arbitrary subcircuit. So for example, down here, I have some subcircuit that's composed of other stuff. There's a whole bunch of compositions in there. And that's in the language, and therefore I can exponentiate the whole thing to some power beta, which could be some user-specified real number. And that's also in the language. So that's how the exponentiation works. The control product is a little bit more interesting. Okay, first of all, you have things like this where you can take 2 of the base generators and connect them with a vertical wire, do the control product, and that's something that's in your language. But then you can sort of nest these things. So for example, in this dashed line, there's 2 boxes here that are being connected, and you can see inside here is a subcircuit that contains kind of a level 1 control operation. And that's where the name hierarchical comes from. Only because you get this kind of hierarchy of nesting, and you can have this sort of nesting depth and so on. But anyway, because this is in the language and this is in the language, then the control product of them is also in the language. And then you can see there's even a 3rd level here. I've got a big box here, and it's being connected to some other subcircuit there. Okay, so that's how that part works. That's the category theory construction, and now I want to tell you about some things that you can do with it, or sort of concrete examples. So first thing I want to show you is a universal gate set for quantum computing. So this is actually the same gate set that I had in the last slide. I've just changed the labels. So this one before was called -1 because it's semantically just the number -1. And then this one has a semantic of a Pauli Z gate. And this last one has a semantic of a Pauli X gate. If you exponentiate those three, then you get this stuff down here. So you get respectively global phases, Z rotations, and X rotations on the Bloch sphere. So if you know some stuff about quantum computing, you know that that's a universal gate set for 1 qubit, because you have 2 arbitrary rotations around 2 different axes. And then if you connect this thing here to an arbitrary subcircuit with this control product, you get, well, exactly what you'd expect. So most people would interpret this as a controlled U, and semantically it is a controlled U. So this is the sense in which these things strictly generalize controlled operations. But of course, you don't have to put this black dot. This could just be some arbitrary subcircuit on m qubits. So, okay, why does that give you universality? Because if I put in the X gate for U, just the 1 qubit X gate there, then I get this Z control product to X, which is a C naught. And then C naught plus an arbitrary universal 1 qubit gate set gives you universality. Next, I want to show so recently there's been a couple papers talking about related things. So this year there was this paper which I think it's actually being presented in this conference, but not in PLanQC if I remember correctly. This is the Quantum Circuits Are Just a Phase paper by Heinen and co-authors. So anyway, they have this primitive, which is, the idea is that you kind of select a subspace, and then you apply a phase in that subspace, and they show how you can use this to construct arbitrary controlled unitaries. And since we're generalizing controls, it's reasonable that there should be a connection, that we can rewrite what we're doing in their language. And this is showing what that is. So this is the property that makes it work. You have some arbitrary control product here, and there's this fact, which is at least semantically true, that if you can write U as a composition, a sequential composition of some circuits A, B, and then A dagger, where A dagger is just the reverse of A left to right and with all the powers negated, then you can kind of split the A's off on either side, and the only part that remains connected with a control wire is the middle section. That holds symmetrically on both wires, so you get this thing. And okay, so a particular choice of unitaries A and B that's kind of the most interesting one is the spectral decomposition, where A is some subcircuit that diagonalizes U. And so, okay, if I write U and V in their spectral decompositions, so in other words, U has these eigenvectors Uj and associated eigenphases theta j, and likewise for V with eigenvectors Vk and eigenphases rho k, then what this operation does in this if-let primitive from the Heinen paper is this. It's essentially doing a switch case statement over the eigenbasis of U and V. And you'll notice that the things that it's, oh, not again, sorry. Yeah, the eigenvectors that it's selecting over are tensor products of the two, and that comes just directly from here. Basically from this you can read off that the eigenbasis of this control operation is the same as if they were just a parallel product. So it has a separable eigenbasis at the cut defined by the control product wire. And yeah, so it selects a space based on the eigenbasis, and then it applies a phase that's proportional to the product of the two eigenphases. These last two bits here I include just because, so okay, in the literature I would say it's folklore that people sort of know this stuff, but I think it's a bit under-discussed. What I'm pointing out here is just a general property of these control operations, and specifically also of normal controlled operations, controlled unitaries and so on. I'm writing here that there's this funny feature that the wires that are acting as the control and the wires that are acting as the target are actually arbitrary. So I'm just pointing that out here. So in this one, we're just kind of, quote unquote, interpreting the top wires as the control wires. So we're reading over the eigenbasis of U and applying operations on the bottom wire. And then at the end here, we're doing the reverse. So we're considering the bottom wires to be the control wires, and we're doing operations on the top wire. But these are really all mathematically equal. So that's why I write equal signs. They're not like connected by some unitary transformation. They really just are the same thing. Okay, now I want to just talk briefly about some potential applications to, I don't know, compilers, circuit optimization, that sort of thing. So on this slide, I'm showing a couple things that I've found in the literature recently that people have been using. So on this top line, we have a circuit identity that's been used in a whole bunch of places, from high-level language design, like it was used in Quipper recently. There was this proto-Quipper with reversing and control paper that uses this. It also appears in low-level circuit optimization, like a paper by Vivian Vandel talking about shrinking adders into logarithmic depth uses this. And this one can be seen as a special case of the same identity that I showed on the last slide, where just the top wire is specifically like a 1-qubit Z gate. But I mean, in general, it can be, m-qubit subcircuit. Speaking of that Vivian Vandel paper compressing adder circuits, this is the trick that ultimately makes it work. It's actually, we've seen the same circuit identity in some previous talks, even just rewritten a little bit. And well, like every identity that involves controlled operations, you can generalize this to the control product. Here it looks like this, where now these wires are n-qubit wires, and you have some n-qubit subcircuits, U and V. And this identity still holds, except with these conditions that basically tell you that U and V have to more or less mimic the Pauli algebra for this identity to hold. And then, okay, lastly, some little examples like this one showed up in a preprint from Craig Gidney like a month or two ago, where he has this funny notation with Z flags. Lots of people that do circuit optimization have their own custom notations, and this is one of them. And he gives a decomposition in terms of topholes and C-naughts, describing what this thing does. But in our language, it does basically this. So it's basically a C-naught that's controlled by a pair of Z gates that are not internally connected. So one way of reading what this gate does is it reads the top two wires in the parity basis, in the computational basis, and if it's odd parity, it does a C-naught on the lower two. If it's even parity, it does nothing. Okay, and then the last one is just like a cute little presentation of Grover, where we have like this is the phase oracle, where I've selected one particular marked state, and then this X gates all connected together is what people usually call the diffusion operator, and then we're exponentiating it, or repeating it the usual number of times. Okay, so that's the end of the talk, and now I'll take some questions. If I can move to the last slide here. Hello? Oh, there we go. Thank you.
Thank you. Anybody else, the final speaker, to come and start setting up? And time for one quick question.
Hi. Do you have ideas of how to reduce these hierarchical control blocks to like standard quantum circuits?
Yes, the short version is we would need a diagonalization procedure, essentially. So I think it's going to be basic. Oh. Okay, it's fine. Well, anyway, I had that identity where you kind of split off subcircuits. And
so you're left with a diagonal bit in the middle, and then you can do...
Yeah, once you have a diagonal bit, then you can reduce it just to normal, like controlled operations like people would normally think of. And so then the only tricky part is how to do this diagonalization. And obviously a dumb way to do it would be to like convert it into a matrix, diagonalize the matrix, and then synthesize a circuit. But that's definitely going to be inefficient because it's exponentially large. There probably is an efficient way of doing it because the circuit is kind of exponentially smaller, but that would involve diagonalizing something diagrammatically. And that's certainly something I'm interested in doing, but I have no idea how to do it. So if anyone has any ideas, please come tell me how.
Okay.
Thank you.
Thank you very much.